Hi, welcome to LD Talks. Here we are going to talk about baseline monitoring. I have mentioned about the baseline monitoring in the second talk of this talk series. So it seems there is some amount of confusion regarding the baseline monitoring, and I have mentioned about the signal grouping in the last lecture. If you haven't seen the last two lectures yet, so I will suggest you go back and check those two. Then you can understand how this baseline monitoring was introduced in the talk. So I will give the links in the card, so you can go back and watch. Okay, now let's talk about the baseline monitoring. So these are the outline. We will first talk about some preliminaries, then we will set up the NR set situation, and then we'll straightly go into the baseline monitoring problem, and we will check the minimum amount of mathematics regarding the baseline monitoring problem. Then we make some observation out of that, and then what is the effects of this baseline monitoring, and we will wrap up our talk with the conclusions. So these are the very basic things we have already encountered in the last 2 or 3 lectures. That's bit rate, baud rate, date rate, and this thing. Here, this is the relation I have written, that is with the RB, which is representing the data rate, and RSym, which representing the symbol rate of, say, the baud rate. Here, all are used as standard notation. So you can pause here and write these slides. I mean, there is nothing much to say about this. Okay, let's go forward. And there is, we already know about the SNR, which is measured in decibel. So here is the well-known expression we have encountered so far. But here is a new term we are going to introduce, that is energy per bit to noise ratio. What is this? That means that if we measure the bit to noise ratio and whatever the energy for the per bit, then that gives the energy per bit to noise ratio. Now the question is, if we can solve any problem, or we can deal any digital transmission system with the measure of the SNR, then what is the point of introducing a new metric? Because in down the line we will see that we have to calculate a term which is called BER, which is bit error ratio. So to calculate that term, we will see that we need that E/BNR day-to-day basis, because there you have to calculate the energy per bit to noise ratio, and from there, if there is some amount of error, and this ratio gives output of that error. So we have to calculate that. Okay, so here is the description of the notations I have used so far. This is N0 is the noise spectral density, and N equals to N naught dot B. So from the definition of the energy per bit, so this is the total signal power, and this is the bit rate. So it represents the ratio of total signal power to the bit rate, gives the energy per bit. So here is the basic algebra I have done. So you can see, if I take this S by N part, so this S by N part represents nothing but the SNR. So here that thing I have written so far. But physically we have to check this, that from this relation we can say that SNR is directly proportional to RB. That means if we increase the RB, it's mandatorily saying by this equation that the SNR will increase. But what this equation is really silent about, that whenever we are increasing the bit rate, we will allow a more amount of noise, and if we allow more amount of noise, that will make the noise spectral density higher, which is making this denominator higher, and eventually the SNR will reduce. Okay, so here we are saying that for the digital communication system, this EB by N naught ratio can be thought as a normalized signal to noise ratio. Okay, so we can roughly equate to the signal power and the time period of the power per energy bit. Here you can see this is the symbol period TS. It is already defined here. So if we take the symbol period multiplied with the power of the signal, it will roughly, approximately, it will give you this EB term, energy per bit. This here. Okay, so as we said, this it's very much needed metric to calculate the PER. So now this is the NRZ recap. We won't spend much time here because we have already completed the NRZ scheme. But what is the goal? So the basic goal is to just transmit with some minimum amount of distortion. And there's an interesting thing we can see here, the match the system bandwidth. What is the goal? As a match the system bandwidth to the bandwidth requirement of the data. I mean, there is a channel in which the this detailed data is fed, and there is a bandwidth we needed to just transmit the data. So we have to match the both of the things so that the transmission makes efficient and there is a minimum amount of distortion results. Okay, so to block, we will see in a couple of minutes that what is the exact circuitry mostly used, or what is the basic circuit structure we use. So here we use the AC coupling. So there is a series capacitor is used to chop off the lowest frequency. So that is DC blocking capacitor, and to transmit the data we must need to convert into the digital signal, as we have already covered in the last talk, and we use a clock to synchronize the data with the clock pulse. Okay, so here we use the square wave as a clock pulse. Okay, so here I have mentioned the TB, which is the bit period, and here I have given the measure of the TB. So now we haven't done the rigorous calculation how we get the power spectral density of NSA, but if you are really interested to, there is a lot of communications books you can check and how to calculate the PSD for NSA. So first say this is the power spectral density for the NSA scheme. This is alpha T, this is a sinc function. The definition of sinc function is measured here. So here, if you look at the plot, I mean, you can see that around the very less frequency, the most of the energy is concentrated in the energy scheme. That's a very basic problem with the polar, entire polar encoding scheme. So if we go beyond 1, then if we go far away from the zero frequency, then we can see that a very less amount of energy is concentrated here rather than this amount of energy is concentrated. So if we normalize the entire thing, then this TBFC is the half power frequency. We have we know that the half power frequency means we are checking the frequency at 3 decibel. So we have covered it in the classes where we have covered about the distortion and attenuation. So this frequency is termed as LF cutoff, which is the low frequency cutoff. So, I mean, whenever the low frequency components get reduced, I mean, it will reduce the SNR and thus it reduces the BR. Okay. By removing the LF components, BR also reduced, and because this bit to error ratio reduced, it's known as the baseline wandering. So I mean, still you can't figure out maybe what is the baseline wandering. That means there is an average line we will take. You will see that, and that will start drifting around the mean. Okay. So, and one thing we should go back. I really missed that. What is the real expression of BER? Here I have mentioned this BER equals to EB by N naught, but for the AWGL signals, AWGL noise, you can see this BER roughly around I mean 0.5 into error function of root over error function of this thing roughly. So you can check in the text. I mean, this is expression of BER. Okay, so this is the circuit. It's mostly for this is the AC coupling capacitor, and the system resistance is R, which is the combined resistance of the source resistance and the load resistance itself. So this is the AC coupled transmission system, what we have talked in the previous slides. Okay, now this figure is quite important. Here we have that represented the NRZ signal. Look, this is I have considered that two polarity, so it is a polar energy. So it's not going back to zero, it's either at the positive voltage and the negative voltage itself. So TB is our bit period, we already know about that. And we mentioned this high pass filtered signal. Whenever we pass this signal, it takes the shape of this form. And we mentioned the low frequency components. The low frequency components is you can get if you just subtract this high frequency components. I mean, if you consider a high pass filter, I mean, what a function of a high pass filter, it will block the low frequency components and allow the high frequency components. So if you have the original signal and if you just subtract these high pass components, filter out components, then you can get this low frequency counterparts. And there is a baseline wonder, it is just nothing. We can see the baseline wandering function is just the 180-degree phase difference with the low frequency signal part. I mean, it's just inverted in sign. So A is here is the notations mentioned here. Okay. So we have to go back and forth for this slide because we will describe this figure in next few minutes. So as we have taken for, say, this is the energy signal, so this is a step function. So the standard step function is defined here, and we are talking about the ST. I mean, this is a one-step function. I mean, if we draw this kind of thing, so this is a one-step function for, say, just a minute. If we this one first, so this is the step function, right? I mean, if okay, so this one is a step function, this one. So either it's 0 or it's greater than 0 region. So there is 1 here. So this is a unit step function. So here you can see the entire spectrum. I mean, if I take the entire spectrum to calculate the entire thing, if I represent this one signal with the UT, and if I want to calculate about the entire signal, that is represented by ST. Let's go back to slide. So now you can see this, we can write the ST in terms of UT. So in between there is a lot of steps we have to do. I mean, you have to take the Laplace transformation and calculating the autocorrelation function to calculate the PST and a lot of things. I mean, we skip those parts and just take the expression for it. So here I have written the part here. Look, this is a U of t, then it's shifted by TB10 and twice of, then 4 times of that, and so on. There's a continuum, there's a lot of higher terms also there. We have discarded those things for now. So here we know this is the ST, we have written this expression, and now we are going towards the high pass component. So we know that this step response, we have whatever we are talking so far, that's a single time constant high pass network. So obviously the step response will be dominated by this exponential t by tau factor, where tau is the time period of the time relaxation. I mean, for any LC circuit, you know this tau is the time constant, is the tau equals to RC. So it's fall by t by RC, so this t by tau. This is the term we have written so far. And now, as there is a shift in this function, there is also the shift is incorporated here also. So okay, equation 4 represent the high pass components, as same the equation 5 represent the low pass component. So as we have seen, this equation, I mean this diagram or this plot, it's mathematically looks like this. Okay, if you just take this equation and subtract this equation, you can see if you just taking common of this thing, and it will come to that point. Okay, so now we are talking about baseline wonder. So from the figure B that we have seen, the average value of in the midpoint of the hyper signal is shown in the figure B. Let's see this thing. So this is the midpoint. So whenever this 0 and 1 change, this line start drifting. If we get a very long amount of zeros or long amount of ones, it starts drifting, as we have seen in this here. As there is a long amount of ones there is a drooping effect already took place. So it start decaying, I mean it start decaying, because there is a AC component and there is capacitor. So there is capacitor discharge expression, or that amount of distortion will be introduced in the signal. Well, yes. So this variation in the average midpoint, whatever I'm telling you, that this line, whenever this line starts drifting between these two dotted lines, then it's called the baseline wandering. The more it's wander around the mean, the more the error will be introduced in the system. The more it's stable, that means the design is more better. So this is the expression from the wandering. As we have said, this is the inverse in signal for the low frequency components, and it's represented diagram T, this one. Now we have come to the part for observations. Here we are talking about the another new metric. We will call it CBD, or cumulative bit difference. What does it mean? That is, this is a difference between the transmitted zeros and the number of transmitted ones. There's nothing else. So here CBDN just represented the cumulative bit difference at the nth bit pattern, whereas this N0 and N1 represent the number of zeros in the pattern up to the nth bit and number of ones in the nth bit. So from the difference we can get this CBD matrix. Well, we will see how this CBD plays role in the baseline wandering, and I mean why we have introduced it. So now what we have observed from the previous plots and equations or whatever, that the magnitude of the baseline wander in this energy scheme that's determined by the CBD and the low frequency cutoff, because if there is a more number of consecutive ones or more number of consecutive zeros, I mean the CBD will change and the lower frequency cutoff will change also. Let's go to the back to the slide. I mean here you can see there is a consecutive 3 zeros, and you can see this lower frequency components start falling, whereas the wandering starts increasing. So from there I can understand, if we take the wandering difference between the number of ones and zeros, I mean obviously this average line will shift around the mean, and obviously that this thing will affect. So from there it's clearly visible in the high pass component that whenever we are getting a consecutive amount of 0, this amplitude getting increased, and whenever we are getting 1, obviously it will decrease. Okay, so baseline wandering changes fastest when there is a consecutive identical digits. I mean, as we have already said, the consecutive ones or zeros or something. So apart from this CBT, I mean, if there is an imbalance between the 0 and 1s, it also creates wandering. So that's why we will see that this is one of the motive, or this is one of the design goal, to make the number of zeros and number of ones as equal as possible. Okay, might it not be equal always, but that's a goal. I mean, we try to make it nearly equal so that there is no, I mean, very less amount of imbalance we will allow in the system, so the system becomes stable. And we already talked about the last point here, that and we will see why we are talking about this last point, that the baseline wander depend on the CBD, only on the CBD, not in the lower frequency component. If we compute the CBD over the very small amount of bit period, I mean, for say we have calculated the CBD for maybe the 1% of the tau by TB term. So there we are getting only the local effect. not getting the global effect or something, because whenever we are just taking the entire range of the data stream, then the lower frequency components will getting more and more introduced, and that's why we can't say that the entire baseline wandering solely depend upon the CBD. It will, if we calculate in a very small range, then it will the small fraction of one time constant. So that means if you can take a tau by t, and take a very small fraction, that will be 0.01 or something multiplicative factor, then the entire baseline wandering depends upon the CBD only. So here we will do some approximations. Here we have seen in the figure D that there is some. Here is the interesting thing is there. Look, there is a this is the substring and this is a substring. This is a 110 and 101. Now the thing is, here is the number of ones and number of 0 in both of the string is same. That there is 2 ones and 1 zeros, and here is also same. But look, the wandering is not same. I mean, if you see the maximum amount it's got reached and maximum amount got reached, and both are different. So for each permutation we are getting the different wandering. That means there is an importance of ordering of the bits also. So changing the that's why I have written the overall change in the baseline ones upon the ordering of the bits. I mean, as we change the permutation of these bits, the wandering level will change. And we all know, as the observation, this is the entire if we look at the equation for W, here this is dominated by this exponential term. So we can say this is not a linear term, this is an absolutely non-linear term. Well, so here is the linear approximation. So we are assuming that the rate of change of baseline wander is constant for say, and because in the previous signal we saw this rule is not really constant. I mean, it's exponentially falling. Here it's exponentially falling, right? But for now, as we are taking the local measures for say, if I look around this small part, for a very small part, for up to this point, if I'm talking about this small thing, so this seems a linear, right? So the baseline wander is in a constant, and for the linear baseline wander, what will happen? The offsets will linearly added irrespective of bit pattern. Whenever we are just discarding the exponential part, we don't really have to care of this ordering of these bits, right? Because the linear terms, you can just sum up the whole terms and taking the average, and things will work like this. So the equation 6, I mean the equation for the wandering, and if you remember, this is some e to the power term, and it becomes like this. This is reduced to, by taking the linear approximation, this entire equation becomes this. And if we take the summation over the entire range, it will keep the CBD and TB by tau. So look, here is the term we have talked about. I mean, if we take a very small region, we will get the local effect only. For this point is depicts in the that equation. This baseline wander only depends upon the CBD. From here we can see these both are the constant terms, and this entire wandering depends upon the CBD only, solely depend upon the CBD. Okay. Here is some plot you just see about this linear approximation. Here the real this exponentially decaying curve, and if we take the 1 minus t by tau, so it becomes very close up to this point. If you see this 1.4.5, I mean, that is the difference is quite small, and it is also very small, and from roughly around 2 or 1.8 or some 0.18 or something, this become getting divergent, and for this region, for in the very lower frequency region, it remains very acute, please say. Okay. So this is eye diagram. This is just a qualitative understanding. I mean, if there is some evidence of baseline wander, we can see there is some amount of scattered dots, right? This, if you increase the thing, here you can see this scattered dots here and there. Everywhere these scattered dots you can see. So these scatter dots represent, I mean, if you check in the CRO, I mean, it's represent that we have the baseline wandering in the system. So now we have come to the last end of this talk, that we will sum up the ideas or concepts we have talked so far. So if we check what is the baseline wander and what is the reason behind it, and what are the results we can get. So it's just a slow variation in the average signal waveform. I mean, if we have some waveform and we just draw a mean around it, which is practically CVD is doing, so then this is a slow variation, that is the baseline. So, and why it's caused, because the low frequency components and the attenuation present in the signal, it happens. I mean, okay, and it will increase the jitter and reduce the bit to error ratio. And now there is a question that if there is a baseline wandering, I mean, how we can control it. Okay, so as we have said before, that we have to control that there is nearly same amount of zeros and one in the system, but the best approach is if there is an alternative 0 and 1s, and then so the effective baseline wandering get cancel out. So obviously in real system it never be possible that every string made of some alternative 0 and 1s. So we need some better encoding schemes so that we can deal the error handling, or such as this data scrambling, encoding this thing to control the CVD and the LF contents. So I hope up to this point we have discussed about the basics, and we set up the NRZ situation. Then we saw the baseline wandering mathematically and qualitatively both, and then we have talked about the approximation, and we have shown that how the entire bandwidth this is entire baseline wandering depends upon the only CVD, not upon the exponential factors, because we have taken the linear approximation. And we have seen in practical situation, if there is a baseline wandering in the system, you can get the scattered dots in the eye diagram, whatever we have seen in the previous slide. So I hope up to this point we're clear, and hope you have enjoyed this lecture. And if you have any questions, you can comment down below, and as I have said, I will give the link of the previous two talks where I have discussed about the signal grouping and baseline wandering. I will give the link in the card. Thank you.